Hi everyone, my name is Imran. I'm a PhD student in Lund University, and I'm here presenting my research in transformer energization using reforming converter. So the motivation for this work is that whenever there is a blackout, even though they are extreme events, they still do happen. And after a blackout, in the restoration process, the restoration involves energizing transformers and lines. In order to do so with converters, we can use two different methods. Either we can connect everything with converter and ramp up the voltage steadily, or we can add different components sequentially and converter at full voltage. So that's called hard energization. Most of the work in the literature is focused on soft energization, and there is little intention to hard energization. Therefore, this paper focus on hard energization using 4 different kind of reforming converter topologies, and we investigate how energization of transformer, which is the main issue in energization process because it requires a lot of inrush current when energizing. So how this interaction between converter and transformer are, and how different line lengths and transformer size affect these interactions. The converter model that we are using is pretty standard one. We have current controller, voltage controller, and modulation as a cascade controller, and then the voltage reference and angle reference are provided by different grid forming architecture, and we have also modeled the DC side of the converter as well with a simple DC energy source which is controlled by a DC current or DC voltage controller. The different grid forming topologies that we have used are group control, virtual synchronous machine, virtual oscillating control, and matching control. I will not go into details of these topologies because of the time, but if you have any question, you can ask later. The test system we have used is a pretty simple one to demonstrate the effects. It consists of a 10 MVA converter with its associated step-up transformer and a 10 kilometer line which is modeled as a pi model, and then a saturable transformer with all the non-linearities and residual flux to show better the inrush phenomena. One thing that I should mention over here that on the current limiters on the converter sides are ignored in this study in order to show the natural response of the converter without any limitations. Now, if we draw the Hemmingsson diagram for this test system, we will have filtered capacitance, resistance, and reactance. Then reactance for this transformer, and then line model, and in the end we have saturable transformer, reactance, resistance, and nonlinear reactance. If we ignore the resistances and model the line as just as a capacitor, we will get the bottom picture, and this shows that in the model we have 2 different capacitances, and each represent one resonance frequency. As the capacitor of the filtered is higher, and as compared to the capacitance of the line, it represents low frequency resonance, whereas the line capacitance represents high frequency resonance. Okay, for the base case, we have 10 kilometer line with a transformer, and we are measuring the voltage and current in phase A at this point. The result shows that with all type of topologies, the current was within the limits of 1.2 per unit, but the voltage were quite high, and in case of matching, it's approaching 2 per unit value. This is because of resonance. As you can see, see there is a lot of second harmonic in all of the topologies, and in case of matching control, we even have 13th harmonic in it as well, which is why it's the worst performer among the three or four categories. And on the other hand, the group it has almost the same voltages and current values like other two, but because of its better decay time, it can be considered as best among the other three. In the next step, we changed the line length from 5 kilometer to 50 kilometer in order to see how the line interaction, line changes can have effect. And what we saw that is for all of the converters has similar trends. The voltage at the transformer started to rise, and at 15 kilometer it has its peak, and after that it start to decrease down. And the 50 kilometer is where the horizons voltage are at maximum, and I will show in the next slide why. And in this case, in this diagram, we are, the line length and the resonance frequency is shown. As it can be seen, starting from the 5 kilometer, the low frequency resonance is of about 110 hertz, and at close to 15 kilometers, it is about very close to the second harmonic, which is why it excites the second harmonic with the converter, and we get the maximum over voltage at this point. After that, the voltage, the resonance frequency is going down, and in the same way, the over voltages was going down as well. In the next step, we change the transformer size from 1 MVA from 12 MVA, and kept the line at constant at 10 kilometers. You can see over here as well, all the transformer, all the converters show similar results, but they had a maximum peak at 4 MVA, which is where there was maximum resonance, and the resonance frequency was close to 10 to second harmonic, and after that it start to decrease, and then it start to increase again in the end, because the resonance frequency is approaching third harmonic, which can be seen over here. That at 4 kilometer, 4 MVA, the resonance frequency was about 102, and then it start to rise to third harmonic at 12 MVA. In conclusion, for this particular system, the system had two resonance modes, one at second harmonic and for the base case, and one at 13th harmonic. And as we increase the line length, the inverse current first increases, and then after the resonance, we pass the second resonance threshold, it starts to decrease, and the voltage at transformers and converter show similar trend. In the same way, for the transformer, only one resonance frequency was changing with changing the size of the converter, and if we compare all four different topologies, the matching was the best. Matching was the worst of all them, and VSM overall performed the best. Thank you for your attention.
I'll ask.
Yes.
You mentioned in one of your slides that with the increase in line length, the resonance decreases. Can you tell me the physics behind it?
Okay. Because resonance is, if you see one of the L over C.
Yeah.
So when you increase the line length, it will L become equal to C. So,
Okay.
any other questions? Yes.
I have a
please.
question. When you say it's, the transformer size,
Yes.
you also change the reactance, the impedance of the transformer?
Yes.
Well, is it the same as on the transformer impedance?
It's same per unit, but
Per
it's
unit.
actually changing.
Okay.
Okay.
And how are you getting second harmonic components?
Yeah, because it's not shown over here because of the time, but in the paper we have shown that when the with transform energization, the dominant resistance, because of the non-linearity, it draws a lot of second harmonic current
Non-linearity where?
in the saturation core, in the transformer core. Yes.
Was there any delay in the grid forming in converters to respond to this energization?
Sorry.
Did you
say-
take into account any delay in
No, there is none.
control?
No, there is no delay was modeled, so we are not looking to any delays. Right?
You don't expect any delay
We didn't no.
in the controls? No.
Yeah, the control there was we haven't modeled any delays in it. We didn't expect it. What we are interested in was the interaction more without any limitation, so we didn't model any delays or current limiters in it.
And what software did you use for the simulation?
The model was in perfect, sorry, not perfectly, but MATLAB Simulink. MATLAB Simulink.
MATLAB.
Thank you.